Welcome to G Fun Facts Online, where today we're talking about the next great leap for humanity, a truly global, unhackable internet. It sounds like science fiction, but it's a future being built right now in labs and government programs around the world. It's called the quantum internet, and the race to build it is one of the most important stories of our time. This isn't just about faster streaming. It's a complete revolution in communication, powered by the weird and wonderful laws of quantum mechanics. The nations and companies that lead this race will not only gain a massive strategic advantage, but will literally shape the future of information itself. So who are the key players in this high-stakes global endeavor? The race for quantum supremacy is in full swing, and three major powers are leading the charge: China, the United States, and the European Union. China has made quantum technology a cornerstone of its national strategy, pouring billions of dollars into research and development. Their most visible achievement is the Mickey satellite, launched in 2016. It was the world's first quantum communications satellite, and it successfully demonstrated the ability to send quantum-entangled photons over thousands of kilometers, even facilitating an unhackable video conference between Beijing and Vienna. On the ground, they've built a massive fiber optic network stretching over 600 kilometers, connecting major cities with quantum key distribution, or QKD technology. The United States, not to be outdone, has responded with significant government-led initiatives. The National Quantum Initiative Act, signed in 2018, committed over $1 billion to accelerate quantum research. The Department of Energy is building a national quantum internet blueprint, with a major testbed already operating in the Chicago area, connecting national labs. The focus in the U.S. is on developing the fundamental technologies, particularly the notoriously difficult quantum repeaters needed for a long-distance network. Then there's the European Union, which is taking a more collaborative approach. The EU launched its 10-year, €1 billion quantum flagship program to fund a wide array of projects across the continent. Their goal is to build a pan-European quantum communication infrastructure called the Euro QCI. Member states like the Netherlands are at the forefront, with projects like QTech in Delft connecting multiple cities in a prototype network. Beyond these giants, other nations are making crucial contributions. The United Kingdom has a robust national program and is focused on developing a commercial quantum communication infrastructure. Australia has a strong research base and a national quantum strategy. In 2020, India established a national mission on quantum technologies with $1 billion budget. And Russia has also identified quantum tech as a national security priority. But this race isn't just being run by governments. The real innovation often starts in universities. Institutions like the University of Waterloo in Canada, Oxford, Harvard, MIT, and the National University of Singapore are the cradles of quantum science, pushing the boundaries of what's possible. And where there's innovation, private industry follows. Tech giants like Google and IBM are building their own quantum computers and the cloud platforms to access them. And a whole ecosystem of specialized quantum companies is emerging. Firms like ID Quantique, Toshiba, and Arkit are commercializing the first wave of quantum security products. Venture capital is pouring in, with over $2 billion invested in quantum startups in 2024 alone. It's a complex landscape of fierce competition and necessary collaboration. While nations want a strategic edge, everyone recognizes that building a global quantum internet is too big a challenge for any single country to solve alone. Now, you might be thinking, if the promise is so great and all this money is being spent, why don't we have a quantum internet already? Well, this brings us to the immense challenges of navigating the quantum frontier. The very same quantum properties that make this technology so powerful also make it incredibly difficult to engineer. The biggest enemy of all quantum technology is a phenomenon called decoherence. Think of a qubit, the basic unit of quantum information, as a perfect, delicate soap bubble. It holds its special quantum properties, like being in multiple states at once, only as long as it's perfectly isolated. Decoherence is anything in the outside world. a stray magnetic field, a tiny change in temperature, even a slight vibration that touches the bubble and pops it, causing the qubit to lose its quantum magic and collapse into a regular, boring classical bit. Protecting qubits from this environmental noise is a monumental engineering task, often requiring extreme cold, just fractions of a degree above absolute zero, and incredible shielding. The next major hurdle is what scientists call the tyranny of distance. In today's internet, we send information as pulses of light through fiber optic cables. If the signal gets weak, we just amplify it. But with quantum information, you can't do that. The no-cloning theorem in quantum mechanics forbids you from making a perfect copy of an unknown quantum state. This means you can't just amplify a weak quantum signal, and the signal gets weak fast. Photons carrying quantum information get absorbed or scattered in the fiber, and this loss grows exponentially. A classical signal can be amplified and sent thousands of kilometers. A quantum signal, sent directly, degrades to nothing after just a few dozen kilometers. So how do you build a global network? The key, the holy grail, is a device called a quantum repeater. Think of it like a relay race for quantum information. But instead of just copying and boosting the signal, a quantum repeater uses a mind-bending process called entanglement swapping. It creates entanglement between distant points without ever sending a single qubit the whole way. But building one is one of the hardest problems in physics today. It requires integrating several technologies that are all in their infancy. You need high-fidelity quantum memories, which are like tiny holding pens for fragile qubits, but current versions can only hold on for fractions of a second. You need highly efficient entanglement swapping, which is currently probabilistic and error-prone. And you need quantum error correction, a way to protect your information from decoherence by encoding one logical qubit across many physical ones. We have the theory, but putting it into practice is another story. Of course, you can bypass the fiber problem by using satellites, like China's Mikius, but that has its own challenges. Maintaining pinpoint alignment between a fast-moving satellite and a ground station, dealing with atmospheric turbulence that can disrupt the signal, and building quantum hardware tough enough to survive the harsh environment of space. Beyond the physics, there are massive economic and infrastructural hurdles. The hardware for quantum communication is currently bespoke and incredibly expensive. Building a global network will require trillions of dollars in investment. This new quantum internet also has to somehow integrate with our existing classical internet, creating complex hybrid networks. And for any of it to work on a global scale, we need common standards and protocols, so a quantum device in Europe can talk to one in Asia. This requires a level of international cooperation that can be hard to achieve. Finally, there are the societal and ethical questions we're only just beginning to ask. There's a real risk of a quantum divide, where wealthy nations reap the benefits of this secure communication, leaving developing countries even further behind. There's the issue of public trust. Quantum mechanics is weird, and if people don't understand it, they might not accept it. And then there's the dual-use dilemma. An unhackable network is great for a hospital, but it could also be used by criminals or authoritarian regimes to evade surveillance. So, given all these obstacles, what does the road ahead actually look like? The quantum internet won't just appear overnight. It will be a gradual, phased evolution. Researchers have laid out a likely roadmap. We are currently in Stage 1, Trusted Repeater Networks. These are the QKD networks that exist today, like the one in China. They use trusted nodes to pass the key along. It's secure, but not truly end-to-end quantum, because you have to trust the node in the middle not to cheat. The near future will bring Stage 2, Preparation and Measurement Networks. These will allow you to send qubits from any user to any other user, but without the ability to store them. This enables more advanced security protocols. Within the next decade, we hope to reach Stage 3, Entanglement Distribution Networks. This is the first version of a true quantum internet, with rudimentary quantum repeaters that can create entanglement between any 2 points in the network. This is where things get really interesting. Stage 4 will introduce more advanced quantum memory, allowing users to store and process quantum information locally. Stage 5 will bring fault-tolerant networks, using quantum error correction to create robust, long-lasting logical qubits. And the ultimate long-term vision, stage 6, is the quantum computing internet. This would be a global network connecting large-scale, fault-tolerant quantum computers, unlocking the full, world-changing potential of quantum information science. It's hard to put a firm timeline on this, but many experts believe the first city-to-city entanglement networks could be a reality within 10 years. A truly global, fault-tolerant quantum internet is likely still several decades away. But the pace of progress is undeniable. We are living at the dawn of the quantum age of communication. The journey from the strange paradoxes of entanglement to the real-world engineering of quantum networks is one of the great scientific adventures of our time. We've seen how nations and companies are in a race to build this future, a future that promises to revolutionize everything from finance to healthcare to national security. But we've also seen the monumental challenges, technical, economic, and ethical, that lie in the path. The quantum leap isn't a single bound. It's a series of difficult, deliberate steps being taken every day in labs around the world. The momentum is building, and the commitment to this quantum future is stronger than ever. This new era promises a world that is more secure, more powerful, and more interconnected than we can even imagine. A future built not on the classical certainties of ones and zeros, but on the strange and beautiful possibilities of the quantum realm. The leap has begun. Thanks for listening to G Fun Facts Online.